All right, in this video, we are going to talk about subgraphs and isomorphisms. This is out of section 1.2 from our book. So, in this class, when we were talking about isomorphisms, we're talking about graph isomorphisms. And so, you may have heard that term in another class before. Abstract algebra, but this is a different, kind of isomorphism that we're talking about. Okay. All right. So, and also, if you're watching this video, we are working out of, and not in the class, we are working out of the book Pearls in Graph Theory, which is an older book, and some of the terminology is a little bit older. So just keep that in mind when you're watching this video. If you're watching it from another class, the terminology that we're using might not, match perfectly with what your instructor is using. Okay, so first off, subgraphs. A subgraph of a graph G is a graph H, such that every vertex of H is also a vertex of G, and every edge of G is also an edge of G. Let's see, that's not quite right there. Every edge of H, this should say, is also an edge of every edge of H is also an edge of G. So there's a typo there. Let me just fix that really quickly. Okay, so here you can see I have a graph G, and then I just show you several subgraphs of G, H1, H2, and H3. So here you can see H1, right, have these three vertices here and these two edges. In H2, I've got these three same vertices again, but one less edge. And then H3, I've got all four vertices, but only these two edges up here. All right, so all three of these are just different subgraphs of this graph G. Okay, and so that's pretty much all we're going to say about subgraphs. All right, so the main topic of this, for the time being, right, we will talk about subgraphs in more detail. But for the most part of this section, we're going to talk about isomorphism between graphs, graph isomorphism. So before we do that, let's make sure that we go back and talk a little bit about bijections and cardinality. So a bijection, or another word that you'll hear, or another term that you'll hear used for that, is one-to-one correspondence. That is a function between two sets that is both one-to-one and onto. Okay. So you may not have used the term bijection in your previous classes or one-to-one correspondence, but you may have just called, a function's one-to-one and a function's onto. But anyway, that's all bijection means, a function that is both one-to-one and onto. All right, and one of the things that we'll need to know about bijections or one-to-one correspondences is that if two sets have a bijection between them, right, there's a bijection from one set to another, then they have the same cardinality. Okay, so for us, we are primarily dealing with finite sets, right, and in fact, right, all of our graphs are going to be finite sets unless otherwise specified. And so for finite sets, it just means that they have the same number of elements, right? If two sets have the same cardinality, they have exactly the same number of elements. So this stuff is going to come into play in this section, so you just need to make sure that you recall some of those facts from your previous classes, specifically 3101. We aren't going to get too fancy about it, so it's not a big deal if you are a little rusty on that. Although, right, if you're a math major, then you need to make sure that you understand these concepts really well. So, but for the examples that we'll look at here, it's really pretty simple. Okay, so that leads us to the definition of isomorphic graphs. So we say that two graphs are isomorphic, G and H are isomorphic, and I'm using this symbol to denote isomorphism. I don't think our book really even uses a symbol, and so again, this may be non-standard terminology. So, but anyway, that's the symbol that we'll use for isomorphism. So two graphs, G and H, are isomorphic if there exists a bijection between their vertex sets, right? So a one-to-one and onto function from the vertex set of G, right, onto the vertex set of H. Okay, so that's number one. You need a bijection. And then that bijection also has to have this additional property that for every pair of vertices, U comma V in G, then U and V are adjacent in G, if and only if F of U and F of V are adjacent in H. All right. So that's what it means. That's the definition of isomorphic. Okay. And that function F is called an isomorphism from G to H. Okay. So, and then one other note about the notation, right? I've denoted this function F as a function from the vertex set of G to the vertex set of H, but sometimes we'll just write F is an isomorphism from G to H. And by that we mean that really it's a bijection between the vertex set of G and the vertex set of H. All right, so sometimes you'll see it written this way, sometimes you'll see it written this way. Okay, it's just a little easier to write this way. All right, so what does it mean for two graphs to be isomorphic? If two graphs are isomorphic, what it really means is that the only real difference in the graphs are the names of the vertices and the edges, right? Now, the edges get their names from the vertices, and so, you are just literally changing the labels on the vertices. There's no other structural changes in the graph. So, essentially, they're the same graphs, just with possibly different labels, okay? So it's kind of like saying two graphs are equal to each other. Okay, so this property right here, you'll see it to referred to as preserving adjacency, right? If you have U and V are adjacent in G, then their images in H are also going to be adjacent. All right, and likewise, this will also preserve non-adjacency, right, as well in the graph. All right, so you'll see it referred to as, sometimes people say it preserves edges or preserves adjacency. So that's the definition of isomorphism. So let's take a look at some examples. Okay, so in these two examples, example 1 and example 2, I'm just going to give you a bijection, all right, from the vertex set of one graph onto the vertex set of another graph, and then I want you to determine whether or not it's an isomorphism, okay, by looking at the properties. All right, so here we have this graph G, all right, and here's the graph H. All right, and what I'm going to do is get a function from one vertex set to another. So, these sets are really small, so you can just list out the function. F of 1 is C, right? So 1 goes to C. F of 2 is A. F of 3 is D. F of 4 is B. F of 5 is E, right? So there's our function from the vertex set of G to the vertex set of H. All right. So there is a couple of things to verify here. Number one, right, the first part is that that function has to be a bijection. So it has to be one-to-one and onto. All right, and here it's really easy to see that the function is one-to-one and onto if you just write it out in this format right here. So this format, this arrow diagram, here I just list the vertices of G, right? 1, 2, 3, 4, 5. Here I list the vertices of the graph H, A through E. And then what I do is just draw the little arrow diagram. 1 gets mapped to C, 2 gets mapped to A, 3 gets mapped to D, and then 4 gets mapped to B, and 5 gets mapped to E. Okay, so there's the arrow diagram, and it's really easy to tell, right, whether a function, if you have this little arrow diagram here, it's really easy to tell if it's a bijection, right? So we can see that it's onto, right? Because for every element, right, over here in the codomain, there is some element in the domain that maps to it, okay? So there's an arrow coming into each one of these. So that means it's onto, right? And then for one-to-one, it's really, again, really easy to tell because if it's not one-to-one, then you'll have some vertex over here, right? Some element over here in the range where there's 2 arrows coming into it, and we can see that that doesn't happen. Okay, so this is one-to-one here. So again, really easy to tell when it looks like this. All right, so that's part 1. This is indeed a bijection between the vertex set of G and the vertex set of H. So that's the first thing that we need to check. The second thing is a little bit more difficult, right? We need to show that for every pair of vertices U, V, and G, U, V are adjacent if and only if F of U and F of V are adjacent in H, okay? So what I do, right, to show this part, what you need to do is, or one thing that you can do, right, this is just one way to do it, but I list out all of the edges of the graph G over here. That's this one. All right, and here I'm just writing these edges as one element and directly followed by the other vertex there. Now, if you're using, in some of the homework problems that I'm going to give you on this, I use 2-digit numbers on some of the vertices, which probably would make people mad, but it was just easier to do it that way. So in that case, right, you might just want to write if there's 2-digit numbers, you might just want to write the edges like 1-10 like that, like 1-3. Because if you write it like 110, right, and that's a little bit confusing as to exactly what that is. However you want to do it is fine. So here I just list out all of the edges, right? So starting with this graph over here, G, right, and starting with vertex 1, which you don't have to start with. To me, it's a little bit easier to keep track of. If there's an order on these things, then it's you can just work through it a little bit more systematically than if you just jump around to different ordered vertices, then it's just easier to keep track of, in my opinion, if you stick with that order. So anyway, I start here with 1, right, and then I say, okay, 1's adjacent to 3, so there's this edge, 1, 3. I have 1, 4, that's this edge right here. 2, 4 is this edge here. 2, 5 is this edge here. And 3, 5 is this edge here. So I just list all of these out right here. That's the first thing that you do. Then I do the same thing over here. List out all of these edges. AB, AE, BC, CD, and DE. So that's all 5 edges here, okay? And then what I do is, for every one of these vertices right here, or every one of these edges, right, where you want to determine where it would get sent by the bijection of the vertices. So vertex 1, right, gets sent to C, and vertex 3 gets sent to D. So that means that this vertex 1, 3 is going to get mapped to CD. So this edge right here. So this edge 1, 3 gets sent to this edge right over here, CD. Okay, so I draw a little arrow. And then I just do that for each one of these vertex. 1, 4, the edge 1, 4, this edge right here, it gets sent to CB, so BC right here. So 1, 4 goes to BC. All right, and then I keep doing that. 2, 4 goes to AB. 2, 5 goes to AE. Right? 3, 5 goes to DE, like this. All right, so that's the process. List out all of the edges of this graph, the one that's the domain. List out all of these edges in the range, right? And then look at where these vertices would get sent to. So when you do that, right, notice that you will get what we get right here is a bijection of the edges, right? You can see this creates a function, right, from the set of edges of G to the set of edges of H. And it's 1-to-1, right? By the same reasoning we said there before, there's not two arrows coming into one of these edges that's in the range, and it's onto, right? Because if I pick any one of these, there is some element of the domain, some edge that gets mapped onto this, right? So that mapping is what's called induced by the vertex mapping. Start with the vertex mapping, right? So you can see where these vertex get sent to, right? Vertex 1 gets sent to C. Vertex 4 gets sent to B, right? So edge 1, 4, the edge between those, has to get sent to BC, all right? So what we get here is a bijection between the edges, and what that means is that adjacency is preserved, okay? All right, so this property that we mentioned back here, if U and V are adjacent in G, if and only if F of U and F of H are adjacent in H. So that's the property that we're checking. All right, so let me take a look. Let me put that down. All right, so this is the property that we're checking, right? So this list, right, of edges is a list of all the pairs of vertices, UV, that are in G that are adjacent to each other, okay? And then when I look at F of U, F of V, right, that's what I'm doing. So when I look at F of U, that would be C. F of V, that would be 3, right? So 1 and 3 are adjacent in G. Are C and D adjacent? And sure enough, they are, right? So that's where that edge gets sent to. So that's what I'm checking right there. I'm checking for all pairs of adjacent vertices in G, are their images, the vertices that they get sent to by the function f, are those adjacent in H, okay? And then going backwards, right, here I list all of the vertices over here. So for instance, I have this vertex, let's say AE, right? I know that that is adjacent in H. Well, looking back at the bijection, right, I can see that, or looking back at the vertex bijection, right, to be specific, I can see that that 2 maps onto A, and that 5 maps onto E, right? So these two are, AE is adjacent in H. Does that imply that these two are adjacent in G? And sure enough, they are right here, right? So with that, we're kind of going backwards. So when you draw this little chart out, right, really what you are doing is checking all possible pairs, right, of UV vertices that are adjacent in G, and seeing that this condition applies. And if this condition applies, then what you'll end up with is a bijection here. All right, so that's it. You just check to see if there's a bijection. Okay, so really all we're doing is checking that adjacency preserving property of isomorphisms. Okay. All right. So the conclusion in this example is that what we've done, we have shown that F is an isomorphism between G and H. We demonstrated, right, hey, here is a bijection of the vertices, right? We showed that it preserves adjacency, right, in the graph, and so therefore this function F is an isomorphism. And the immediate conclusion, right, is that the graphs G and H are isomorphic, and that's what you have to do, right, to show that, to show that two graphs are isomorphic, or it's one way to show that they're isomorphic is to demonstrate that isomorphism between the two. Okay. All right, let's take a look at example 2. Or actually, before we go into example 2, this theorem here is kind of the theorem behind the scenes that that we are using here. And in particular, right, in example 1, we ended up with not only a bijection between the vertex sets, but also the edge sets, right, here. And that's what I said, that's what you need to be looking for. If you get a bijection, then you're going to have an isomorphism. If you don't get a bijection here, then you do not have a graph isomorphism. All right, so the theorem here says graphs G and H are isomorphic if and only if there exist bijections between the vertex sets and the edge sets, such that for every edge in the edge set of G, the function f of v maps the endpoints of E to the endpoints of f sub E of little e. Okay, so in other words, you get a an edge preserving situation here as well. Okay. So if you have two bijections that do that. So again, we're basically using this direction, right? We're showing that, hey, there is this bijection by checking all of those edges are mapped the correct way, and then we're getting that G and H are isomorphic. Okay. So I'm not going to go through the proof of this, but it's not too difficult. But hopefully you can see just by by the explanation up here that when I make this little chart, I am checking to see if this property is preserved. Okay. All right. All right, example 2. Same problem. We want to, we are given a bijection, and we want to determine if it's an isomorphism or not. So essentially same exact problem from last time, just a different example. So the bijection we're given is that f of 1 equals C, f of 2 is A, f of 3 is D, and f of 4 is B. All right, so 1 gets sent here to C, 2 gets sent to A, all right, 3 gets sent to D down here, and 4 gets sent to B. over here. All right, so just verifying that the, oops, this is messed up again, sorry. I think that is a copy and paste error. Yes, it is. Okay. All right. So let me just, I'll have to fix this later. So let's just do it this way. So f of 1 equals c. F of 2 equals a. F of 3 equals d. F of 4 equals b. All right, so there we go. So just want to verify that this is a bijection, although it's really easy to see, right? So f of 1 is c, so that would go here. And f of 2 is a, so that would go here. F of 3 would go here. And f of 4 would go here, right? So finite set, we can see, hey, this is a function from the vertex set of G over to the vertex set of H, right? And it is definitely onto, right? Because every element of the range, right, that is the vertex set of H, is the image of some element of the domain of the which is the vertex set of G, right? In other words, there is some number, some vertex that when I plug it in the function, I get any one of these things as the output. So it's onto, also one-to-one, right? Because I don't have two different elements of the domain that are mapping to the same point in here. In other words, in the arrow diagram, right, there's not two arrows from two different things in the domain going to the same thing in the range, right? So this is a bijection. All right, so that's the first thing. We just need to verify that. And then this is the slide with the wrong bijection on there. And that is, let's just make sure that's the one. Okay, yes, that's the one we looked at before there. So that looks good. All right, so again, on this part, we are checking about the edge preserving properties, right, of this bijection. And so what we would do is, again, list out all of these edges here, right? So starting with the graph of G, I can see it has this edge 1 to 2, this edge from 1 to 4, this edge from 2 to 3, this edge from 3 to 4, right? Over here, right, again, list out all of the edges. I have an edge between A and B, A to C, A to D, B to C, and C to D. All right, and right there, you really don't have to look at this much to know, hey, there's no way that there could be a bijection, right, between this set and this set. That's just never going to happen because, right, going back to this fact up here, right, two sets have the same cardinality if and only if there exists a bijection between the two sets, right? And remember, we said for finite sets, right, the cardinality is just the number of elements in the set. So, so therefore, there is no bijection between those two sets, okay? And but let's run through how the induced map on the edges works. So 1 to 1, 2, the edge 1, 2 would go to AC. So I draw a little arrow through there. The edge 1, 4, that would go to CB or BC, which is right here. The edge 2, 3, right under the induced mapping, would go to AD, which is right here. All right, and then the edge 3, 4 would go to BD. Okay. But that's an issue. You can see, right, that B and D are not adjacent in H. Okay, so what I've got here is I've got some vertices that are adjacent over here. 3 and 4 are adjacent in G, but where they get sent to, right, 3 gets sent to D, right, and 4 gets sent to B, right? So, but these two are not adjacent. There is no edge, right, from B to D. So this is not even a function, right? If you're talking about this as being the domain, you want this to be the domain. It's not a function on the edge set, right? Because there's an element of the domain that doesn't get sent anywhere, right? That induced relation is not even defined here. Okay, it's not in there, so that's a problem. Not only that, right? There's some things over here, right, that don't get mapped onto, right? AB and CD do not get mapped onto. So let's take a look at that. The edge AB, right? There's A and B are adjacent over here, but when you look at what gets sent onto A and B, all right, A, that would be 2 and B would be 4. So 2, 4 are not adjacent over here. So you've got some vertices over here, right, such that their preimages are not adjacent over here. All right, then what's the other one? CD, right? That's adjacent in this here. And so when I look at what maps onto C, that's a 1, right? And 3, right? So if I look at C and D, right, they are adjacent over here, but what gets sent onto those, 3 and 1, that's not adjacent over here, okay? All right, so again, that's an issue here. So this is not a bijection, right, between the edge sets, and you'll never get really a bijection between there, okay? So that's what it's going to look like when something you have is not an isomorphism. Okay. So the conclusion is the function f is not an isomorphism, right? And just by the work we've done in this problem, right, we don't know about isomorphism. Just because the function that you tried, the bijection that you tried to use, is not an isomorphism doesn't mean that there doesn't exist an isomorphism between the two. So really, we haven't really concluded anything other than f is not an isomorphism here. Just so because you have you tried some function that was not an isomorphism, right? There's plenty of other functions that you might try to get an isomorphism. So at that point, G and H may or may not be isomorphic. Okay. Now, in actuality, they are not isomorphic, and if you follow what I set up here, right, there's no way you're ever going to get a bijection, right, between a set with 4 elements and a set with 5 elements, right? Yeah, because then they would have to have the same number of elements, and they don't. Okay, so these are not, in fact, isomorphic. But just because one isomorphism or one bijection isn't an isomorphism, right, don't automatically jump to the conclusion that the two graphs are not isomorphic. You can't do that. All right, you'd literally, if you're going to do it the brute force way, you'd literally have to show that no, that no bijection is an isomorphism, right? And that way, it's just not feasible to do. There's way too many bijections between sets, so you'd have to check all of them. So in general, that's not what you want to be doing. All right, so what do you want to be doing, right? Some ways to tell that that graphs are isomorphic, right? First off is that isomorphic graphs have to have the same number of vertices, okay? And why is that? Well, it's because, right, an isomorphism is literally a bijection, right, between the vertex sets. And if you have a bijection between two sets, well, then they have to have exactly the same number of elements. So remember, we're talking about finite sets here, so isomorphic graphs have the same number of vertices. So if you had a graph with 5 vertices and another graph with 6 vertices, boom, automatically, right, they are not isomorphic. All right, the next property is that isomorphic graphs have the same number of edges. And we saw that, right, when we were running through that little process to see if a bijection between the vertex sets also gave us a bijection between the edges. So if it does, then you had an isomorphism, right? And so since you have a bijection between the edges, then they have to have the same number of edges, right? So one way to tell that two graphs are not isomorphic is if they have a different number of edges. If one graph has 5 edges and the other has 7 edges, well then automatically you know that those two graphs are not isomorphic. All right, so another property of isomorphic graph pairs is this. So let F from G to H be an isomorphism, and then let V be in the vertex set of G. Then the degree of F of V has to equal the degree of V. Okay, so suppose that you had a vertex right over in G, and let's just say it was degree 3, right? So let's call this vertex V. And let's say it was degree 3, right? So what that means is that there are 3 other vertices in G that are adjacent to V, right? So the picture would look like this. And this is only part of the graph, right? I'm just drawing V and the vertices that it's adjacent to. So you'd have exactly 3 of those, all right? So then what we would do is look over at where those vertices would be sent under the map F, right? So under the map F, then you'd have F of V somewhere. And then F of V1, F of V2, and then F of V3, right? So you may say, well, how do I know that all of these vertices, V, V1, V2, and V3, how do I know that they all get sent to different vertices of H over here? Maybe V1 and V2 get sent to the same vertex over here. Okay, and that can't happen, right? Because F is a bijection, right, between those two. If V1 and V2 got sent to the same vertex over here, then your bijection between the vertex sets would look like this. It wouldn't be 1-to-1 anymore, right? So these 4 vertices are 4 different vertices in H. All right, and not only that, remember one of the properties was that whenever 2 vertices are adjacent in G, right, then their images over in H have to be adjacent. So because V and V1 were adjacent in G, well then that means that F of V and F of V1 are adjacent over in H. Since V and V2, right, were adjacent in G, well then they have to be adjacent over in H, right, because of the isomorphism, that adjacency preserving property. All right, here are 2 vertices that are adjacent in G, V and V3. So F of V and F of V3 have to be adjacent over in H. Okay, so you can see that that F of V has degree 3 over here. And now you may say, well, look, how do I know that over in H, right? How do I know that there's not some other vertex over here, right, that is adjacent to that? That would make the degree of F of V bigger than 3, right? And this one has degree 3. Well, that also can't happen, right, because of the backwards property. Right here I would have 2 vertices in in the image, right? F of v and whatever this is, right? Remember the property for the edge adjacency preserving, right, is that this property here says that f of u and f of v are adjacent in H if and only if u and v are adjacent in H, right? So that would mean if this were true, if there was one like that, that would mean that there was some other vertex over here in G that was adjacent to V, but we know that can't be, right? Because we know that the vertex of V was, or the degree of the vertex V was 3, right? So that can't happen. That means that this situation can't happen over here, right? So that means there has to be exactly 3 vertices in H that are adjacent to f of v. Okay. So that that 3 is not a magic number, right? You can do that for any number, right? I could have just said extend that proof to n, right? If this is degree n, right, then I have v1 all the way out to vn adjacent over here, and f of v would be adjacent to all of those, right? F of vn over here. And that's it. There can't be any others because of that same argument. They would pull back to another vertex, and that would make this degree n plus 1. Okay. All right, so that's the idea behind that theorem there. So that's a very, very helpful theorem, right? When you're trying to construct isomorphisms between graphs, figure out isomorphisms, then you know, right, that that if you're trying to figure out where the bijection should send a certain vertex, it has to send it to a vertex over here that's of the same degree. Okay, can't raise the degree or lower the degree. So that gives you a really good hint about where things go. You can kind of narrow down the possibilities of which vertices go where in the bijection. And then all you have to do is check to see if that works. All right, as a corollary of that, we have this theorem that says let f from G to H be an isomorphism and let E be an edge of G. Then the endpoints of edge f of E have the same degrees as the endpoints of E. All right, so let's say I have some edge in G. So there's some edge E that they're talking about. And let's say these vertices are called U and V. And let's say the degree of U is 5. Let's say the degree of V is 3. Okay. So over in H, you would have f of v, right? Because we have an isomorphism between these two graphs. And f of u. So u gets sent over to f of u, v gets sent over to f of v, and then we know, right, what the degree of f of v is by the previous theorem, right? We know that the degree of f of v has to be the same as the degree of v. So it has to be degree 3. And likewise, right, we know that the degree of f of u, right, has to be the same as the degree of u, right? So the degree of f of u equals 5, right? Same as the degree of u over here. Okay? So that's what this theorem says. Hey, it sends edges, right? The edge is going to get sent over to an edge that has this, whose endpoints have exactly the same degrees. So again, that helps to provide a clue if you're trying to find an isomorphism between two graphs. Then you know roughly, right, the possibilities. It helps you narrow down the possibilities. You know that the endpoints have to have the same degrees wherever that edge goes. Okay. And we'll use this in a minute. We'll show how to. We'll use this to show that two graphs are not isomorphic. All right, isomorphic graphs have the same degree sequence. Again, that's just a corollary, right? If the image of the vertices, they all have to have the same degrees, right? So, and you have the exact same number of degrees if two graphs are isomorphic. So, straight away, that tells you that isomorphic graphs have to have exactly the same degree sequence. Okay. All right, so one thing you don't want to fall into the trap, right, is that of saying that if using the converse, right, of any of these facts right here, because they just are simply not true. Okay. All right. So the fact that a graph has the same number of vertices, the same number of edges, and the same degree sequence as another graph does not imply that the two graphs are isomorphic. So that's what I'm talking about. Don't fall into that trap. Say, you know, that's true. It's easy to do that, right? But you have to make sure that you don't do that. And so here I have an example of two graphs that have exactly the same number of vertices, exactly the same number of edges, and exactly the same degree sequence, but these two graphs are not isomorphic. Okay, so just verify this with me here, right? You can see that each graph has 8 vertices, right? 1, 2, 3, 4, and then 1, 2, 3, 4 here. So 8. Same thing over here. 1, 2, 3, 4. 1, 2, 3, 4 here. So they both have 8 vertices. They both have 10 edges. All right. So 1, 2, 3, 4 around the outside square. 1, 2, 3, 4 around the inside square. So that's 8. And then 9 and 10. All right, and then same thing here. 4 around the outside square, 4 edges around the inside square, and then 2 additional edges gives us 10 edges altogether. All right. So same number of edges, and now let's check the degree sequence. Right, we can see that this graph has degree 3 here, a degree 3 here, and a degree 3 here. So 1, 2, 3, 4 threes. And 2, 2, 2, and 2. So 4 threes and 4 twos. This graph, right, this is a vertex of degree 3. Here's another vertex of degree 3 here, a vertex of degree 3 here, and a vertex of degree 3 here, right? So 1, 2, 3, 4 threes. And then this is a degree 2, this is a degree 2, this is a degree 2, and this is a degree 2. So you can see, right, they both have 8 vertices, 10 edges in the same degree sequence, yet they are not isomorphic. Okay. So how to verify that they are not isomorphic, right? So to verify that these things are not isomorphic, right, we are going to use that fact about if I have an edge in G, right, then its image over here, right, whatever edge it gets sent to by that induced mapping, the endpoints have to have exactly the same degrees. Okay. So the trouble, right, starts in here. If I look at this graph over here, and this edge in particular, right, this edge goes between 2 degree 3 vertices. Okay. So it goes between this one, degree 3, and this one's degree 3 over here. And then I've got another edge like that down here. Here, this one is degree 3, right? This one is degree 3 here. All right, so I have 2 different edges whose endpoints are both degree 3. So 2 edges with endpoints both degree 3. The issue, though, is so what has to happen if you have an isomorphism between these two, then these 2 edges need to go to 2 different edges that have that same property, right? the endpoints of the edge have to be both degree 3. But the issue is that H only has one such edge. All right. So right here, if I look here, this edge goes from degree 3 to degree 3, right? All right. And then this one over here is degree 3 to degree 3. Actually, that's right. So actually, that's what I have here is incorrect. But the issue is that this one, right, over here. So this, again, another typo. Sorry about that. But the issue is that this one has 3 of those, right? If I look here, this has degree 3, degree 3. These connect 2 degree 3s right here. So this one only has 2 of those, right? All of the other edges, right, go between degree 2s and degree 3s. All right? So that's a problem, right? That those don't match up, right? So the question is, all right, one of this, say this edge goes to this edge over here. This one gets mapped over here. That leaves no other edge in this graph that gets sent to this, and so that's a problem. All right. So so yeah, even though, sorry, I messed up on that. I'll fix that when I put those in slides in there. But this should say H has 3 such edges there. Okay. So anyway, I'll fix that before I load that up. All right. So that's about it on this one. And if you have any questions, let me know about this section. In the homework, I'll give you some graphs. Actually, I should probably pull that up right now and talk about that. So let's do that. All right, just give me a second here. Okay, so here is homework number 3. It says the relation is isomorphic to is an equivalence relation on the set of graphs below. Find the equivalence classes of this relation. So I think there's 6 graphs. Yeah. So there's 6 graphs, and it is an equivalence relation, being isomorphic, and so that will divide these, that will partition these, graphs into sets, right? And so, for instance, you might work through this. There's 6 graphs: G1, G2, G3, G4, G5, and G6, right? And your job is to decide, find the equivalence classes. So your answer might look like this in the end. Maybe you find that G1 is isomorphic to G5 and G6 is isomorphic to G2, and then G3 and G4, right, are not isomorphic to any of those things, right? So your equivalence classes would be G1, graph 1, graph 5, right? G1, G5, G2, G6, and G3 and G4. Okay. So your answer would look something like this. Remember that being an equivalence relation, I tell you, hey, is isomorphic to is an equivalence relation, right? So that's reflexive, symmetric, and transitive, right? So obviously, all right, all of these are symmetric to themselves, right? So of course are isomorphic to themselves. So you don't have to check that. It's symmetric, right? So if G1 is isomorphic to G5, then certainly G5 is isomorphic to G1. It is also transitive, right? So for instance, say you found that, say it didn't look quite like this, and you found that G4 was also isomorphic to G5. Well, then since it's transitive, right? It's an equivalence relation. It's automatically going to be isomorphic to G1. So I think that was supposed to be G4. So you found G4 was isomorphic to G5, and you already knew that G5 was isomorphic to G1. Well, then there's no need to check that G4 and G1 are isomorphic, right? Because, it's transitive. Through composition of these isomorphisms, you're going to get an isomorphism from G1 to G4. So make sure, to exploit those properties there. So to save yourself from doing some work, you have to do less work that way. All right. So that's one part that I want you to divide these up into equivalence classes, right, of isomorphic graphs. And then for each distinct pair of isomorphic graphs, give an explicit isomorphism between the two graphs and prove that it is an isomorphism. So I guess actually you do have to do some of that work there. So I ask for an explicit isomorphism. And then if you have a pair of non-isomorphic graphs, state why they are not isomorphic. All right, so using those things that we talked about in this lecture, if they have a different number of vertices or a different degree sequence or a different number of edges, right? And or that trick that I showed you about how with the mapping of the edges in that next to last example that we went through. All right, so that's it for this one.